Okay, so what happens now when we stack lots of loops on top of each other? So not just a loop like this, but lots of loops. And so this shape is called a solenoid, basically a coil of wire. There's other shapes of this type of thing. You can wrap it around into a donut shape, which is called a toroid. But basically this is how we make an electromagnet, where we have a very strong magnetic field inside the coil. So this long straight wire is bent into a coil shape and making an electromagnet. We can figure out the direction of our magnetic field by the right-hand rule. So again, I'll grasp the wire with my thumb, and the direction that my fingers go is the direction of the magnetic field. And so, like I said, this is how we create an electromagnet. So this is basically just a nice iron nail, nothing particular about it, that I've wrapped a bunch of wire around, just haphazardly. It's not particularly pretty, but the idea is that this can be created into an electromagnet. So here's the big nail originally. It's made of, got some iron in it, so it's magnetizable. And so if we look at it originally, then there's no particular magnetic property, that it doesn't pick up these metal paper clips, these steel paper clips, with no attraction whatsoever. However, if I complete the circuit and hook this guy up, and I can actually feel it vibrating a little bit in my hands, but basically it turns it into an electromagnet where I can start picking up stuff. And then as soon as I disconnect the electricity, the electromagnet is gone. So this is exactly how, like, an electromagnet in a junkyard works. This is exactly how the electromagnet in an MRI machine works. It's basically we are sending current through a coil such that it creates a magnetic field. So that's all you need, is an electromagnet. So this means the electric field lines on the solenoid are nearly parallel and uniform on the inside. It doesn't really depend on how close you are or far from the actual coils. The magnetic field is the same within the entire coil. And the exterior is non-uniform and much weaker. So there is some magnetic field on the outside, but not much. The real strength of the magnetic field is inside. Now we're going to look at the equation for the magnetic field within a solenoid shape. And so it looks very similar to the other equations that we've used. We have the magnetic strength of the magnetic field, and we have mu naught, still the permittivity free space, and I is the current. But this new term L is defined as the number of lengths, another number of turns per unit length. So it's the total number of turns, so N total, over the total length. So the total length is down here, is the total length of the solenoid. And in problems, sometimes you're going to be given the number of turns per length, or the total number of turns and the total length. So either way should work. So then we have mu naught capital N over length times my current. So basically, this formula is derived from Ampere's law, where basically we're taking this rectangle as the path we're going to take when analyzing it, and we get that as the magnetic field using Ampere's law. So basically the solenoid, here we have a solenoid of length 1.23 meters, and here you can see a nice picture of a solenoid immersed in a liquid with those iron filings, and you can see the magnetic field pretty clearly, and it looks roughly the same strength throughout the whole length of it. So the diameter is 3.55 centimeters, and there's no diameter in the formula, so we don't really care about that number, but we do know it has a total number, so it's going to be capital N and the current. So that's N, and this is L, so we're actually going to use the mu capital N over L times my current to find the magnetic field. Now we just put those numbers in, and you should be able to do that. And so that's your challenge for this time, is just put the numbers in the formula and see if you can come up with the right answer. So we put the numbers in, and we end up with 24.2 milliteslas. So that's pretty strong with just 5 amps. We're many orders of magnitude greater than the Earth's magnetic field at that point. And online, since I know we covered a lot of formulas in this chapter, is a nice PowerPoint, one-slide PowerPoint with all of the equations we've used. We have talked about the force on a charge, the force on a wire, and then therefore the torque, on a loop, and the force per unit length on a pair of wires due to the magnetic field that one creates on the other. And for a charge moving in a circle, it moves. For a charge moving in a magnetic field, it moves in a circle. So that circle has a radius and a period. And then we talked about basically the sources of the magnetic field from a wire, from a loop, and from a solenoid. So which formula you use depends on what shape, and it should be pretty obvious from the problem what shape you're dealing with.